welcome everyone for this IABSE webinar. We are here today to hear about Lille Langebro, which won the Structural Award in Denmark in 2021, and arranged by the Danish group of IABSE. You know, IABSE is an organization with over 3,200 members in 100 countries. And our mission is to exchange knowledge and advance the practice of structural engineering worldwide. And I forgot to say that this webinar will be recorded and is transmitted live. So now you know that as well. And we'll have a Q&A at the end of the session. So please write, if you have any questions, please write them in the Q&A box. But as said, this is IABSE, and the way we are exchanging knowledge is via these webinars as we're having here today, and via our conferences. We just had a conference in Istanbul on long-span bridges, and in September we'll have one in New Delhi on sustainable development. And I promise to say that at the moment we are open to submission of abstracts for the conference in Manchester. Another way of exchanging knowledge is via publications. We have our journal, of course, Structural Engineering International, and then we're also publishing bulletins. For instance, we've just published a bulletin about the bridge collapse in Colombia. And I think we had a webinar on that one as well. I would encourage you to see that. It was very interesting. IABSE, we're organized in national groups as the one in Denmark, and then task groups. And we have these 6 technical commissions on the topics you see here, and over 30 task groups on different investigations where experts and members from all over the world is participating. So yeah, sorry, I think I will go on about that. Also, we have this Young Engineers program where you can get a discount on a student membership, and then get most of the advantages of being like a member of IABSE. And in the local national groups, different events are being held. In Denmark, for instance, we'll soon be going on a technical visit to the new Storstrøm Bridge. And the last thing is that we have this possibility of e-learning. And that was my short introduction. As I told you, what we'll be hearing today is a presentation about Lille Langebro, which won the Danish Structural Award in 2021. And here to present that is Simon and Michael. So I think I will leave the floor to, I think Simon was the one to start. Yeah.
Thank you very much, Jan, and good afternoon, everybody. Yes, our presentation is about Lille Langebro in Copenhagen. I imagine quite a few of you have seen this structure, and hopefully we can give you some insight into how we went about designing it and building it. This is the structure of our presentation this afternoon. I'll be doing the initial part. Michael is the mechanical designer. He'll be giving us some detail about how the mechanical design of the bridge works. And then I'll finish off with some of the construction aspects. So I'm sure many of you are very familiar with Copenhagen and the location of the bridge, which is very central on Copenhagen Harbour, next to the Langebro. So this is the main artery through the city, Hans Christian Andersen Boulevard. Very, very busy road. Not very pleasant for cyclists and pedestrians, and raised up above the surrounding land. Our bridge connects the north and the south part of the harbour from this location A to B, and was commissioned by Real Dania, who are the client for a new development called the Blocks project, which has been built next to the bridge location. And this is the timeline for the project. So it started off with a competition that was launched by Real Dania back in 2014. Seems like this is crazy that it's several years ago now. Doesn't seem so long ago. Bureau Happold entered the competition with architects Wilkinson Eyre and Eden Consulting. We were lucky enough to be chosen as the winning design. We went into production mode, and the bridge was tendered in 2016, and the construction started in 2017. It was due to be completed in 2018, but for reasons which I'll go into, it wasn't finished until 2019. So this is the team. As I say, the design team was made up of Bureau Happold, Eden Consulting, and Wilkinson Eyre. We also had some local consultants, NIRAS, helping us with the ground engineering and the substructure design. Urban Agency were local landscape architects, and Spears & Major were the lighting designer. We initially worked direct for Real Dania, but then we were novated to a joint venture of Mobilist Denmark and Hollandia. And at the end of the project, the bridge was gifted by Real Dania to the Copenhagen municipality. Right, so into the competition design. This is a bit of a summary of the brief that we were presented with. It's a pedestrian and cycle bridge, really trying to create a much more convenient and pleasant route for those users than the existing structure, existing Langebro. The initial budget was 90 million Danish kroner, and the length is 160 meters. We had to provide a 35-meter wide navigation channel in the center of the harbour, and there were clearance requirements when the bridge was in its closed position as well that we had to adhere to. The required width was 3 meters for pedestrians and 4 meters allowing two-way cycle traffic, so 7 meters altogether. So this would be a simple A to B route. The architect's very keen to have a low-level crossing without structure projecting too high above it, partly because of the adjacent structure. We didn't want to compete architecturally with that, but also to allow views over the harbour. So in order to meet the clearance requirements for the bridge in its closed position, and also to align with the desire lines on either side of the bridge, we came up with a curved alignment in plan that was raised up to allow the clearance that was required for the bridge in its closed position, which allows some of the smaller craft to travel without the bridge being opened. And doing that also provided views of the adjacent sites. And this is the bridge images from our competition entry. So you see it has this curved shape. And it's a dual swing bridge. So it's two sections which open by rotating to allow vessels through. We call this section 1, 2, 3, 4. So section 1 and 4 are static, and 2 and 3 rotate. The inspiration for the bridge is the flight of a bird as it flaps its wings. And you can see how that also manifests itself in terms of the structure with this twisted form of the main structure along the edges. This made sense architecturally because it gave a nice feel to the structure, but also structurally because we've made sure that the greatest depth is provided in the sections that have the greatest structural demand. Okay, so a bit more into the detail of the structural design. It's quite a complicated drawing, which shows the key elements of the bridge, and you can see the navigation channel 35 meters wide down the center, which is bounded by vessel collision protection system on either side. We have 4 piers actually in the harbor. These bear down on the glacial till, so they don't have piles. They're just built within cofferdams. The upper section is concrete, and the support is founded on top of that. We have abutments at either end, which are fixed down to piled foundations. There are movement joints either side of the rotating sections, and in the middle is a moment connection, which is something that Michael is going to go into a lot more detail about. So I won't spoil his section too much, but sufficient to say that the moment connection, rather than providing a pin in the center, actually clamps the central sections together. And that has great advantages in terms of keeping the structure as slender as possible, which was very much our aim. Try to avoid having lots of structure above deck level. This is an image of one of the rotating piers. We have this sort of quadrupod arrangement of inclined members on top of a slewing ring, which allows the rotating to take place. And you can now start to see the main structural elements along the edge of the bridge, which are triangular in shape, and they are twisted as you go along the bridge, so that the outer skin of those members is doubly curved. Here are several different sections which show that again. So it's actually a ladder kind of structure with these triangular main beams on the outside, a series of troughs which connect in between, and a steel deck plate, orthotropic plate, stiffened plate deck. Lots of different details. One of the most critical details is actually this little innocuous weld detail here, but that is the tip of the triangular section, and it was very important to try and get a very crisp line to that, to really emphasize this sort of sweeping nature of the bridge. So we spent a lot of time working on that and doing mock-ups and tests in the factory and so on, try and get that just so. This is a fabrication model of the bridge, which shows some of the elements in perhaps a little bit more clearly. Now, we know that other bridges in Copenhagen and elsewhere have had lots of problems with their response to thermal effects. So this was studied in a great deal of detail. And our bridge was by no means easy to analyze from that point of view, having such a complex geometry. So we undertook quite a detailed shading study of the bridge. We looked at it all times of day and all times of the year to see what parts could be heated and which parts would be shaded. And we ran multiple load conditions to try to determine the worst case deflections and displacements at the joints of the bridge, where we wanted to make sure that we'd allowed enough tolerance so that when the bridge came back into position, it would align correctly. So this was an element which we spent a lot of time on, and actually I think we're all glad that we did. We didn't seem to have had any problems from that regard. Being a cantilever, the sections have to have quite a lot of precamber applied. So I think this is section 2, which has got most of the equipment in it, and that had to have a 250 millimeter precamber. There is a counterweight in the back of these rotating sections, where we filled the hollow sections up with concrete to help to counterbalance it. And the process of appointing a contractor was very interesting. Actually, there were 2 competing contractors in the end, and part of the tender process was for them to produce a mock-up of a bridge section to show the quality that they could provide. For example, with this weld detail that I explained at the very tip of the section. So we were able to look at the 2 mock-ups side by side next to the harbour, and that formed part of the tender evaluation. As I say, in the end, it was Mobilis and Hollandia who were selected. Okay, so that's a little bit of the background to the design. I'm now going to hand over to Michael to speak about mechanical design.
Hi everybody, I assume you can see me and hear me clearly. So yeah, I'm going to talk about the mechanical elements associated with the bridge operation, and as Simon said, kind of the key element of innovation and the trickiest bit is this moment connection between the 2 moving spans. Taking a look at the, trying to work out why it's not moving forwards. There we go. Helps if I'm in the PowerPoint presentation. So taking a look at the 2 moving spans inside elevation, we need to be providing a rotational support. Looking in plan view, one span rotates anti-clockwise and the other span rotates clockwise. The clockwise, so the right-hand side, moves away first by a few degrees before the left-hand side starts to rotate. And the way we achieved that then was with 2 very large slew bearings, and that was mounted on top of the concrete pier on a big steel plate, and then you can see the blue elements, the outer element of the slew bearing, and that's held statically, and then the inner race of the slew bearing is attached to the underside of the bridge, and that's then driven by 4 electric motors. If we look here, you can see on the left-hand side, there's a cross-section through various different types of slew bearing. The one that was used on this project was the lower right of the 4 images, and you can see in the right-hand image that there's a drone image of the piers before the bridge was installed, and then you can see the four drive motors, and then there's 2 red gears, which is what's monitoring where the bridge is rotationally. There's sensors attached to them. So that's how the bridge is supported at the 2 piers and allowed to rotate. We also have to support the bridge at its very ends, so where it meets with spans 1 and 4. There's going to be, when it's unsupported or when it's needing to swing, we need to be able to release those ends, and in doing so, we're going to generate the deflections that Simon's talked about due to thermal and dead load effects. So we need to provide a support at the ends. It's restrained axially at the slew bearings, so we also need to be able to accommodate thermal movement at the joints between the static and the moving spans. And you can see here there's two curved red lines. That's where that joint occurs. And the way we achieved that was to provide these orange sockets on the static span. And then if we zoom in, so there's a orange socket in two places just next to the main structural members. And they guide in a pair of wheels, which you can see in green towards the center of the image. There's two wheels mounted on a single axle to allow them to share the load. And that rides into the socket as the bridge swings round. So it could come in slightly too high or too low. And the wheels and the socket guide the tail end of the bridge in as it rotates round. There's another view showing the two wheels and the socket. So we've got thermal expansion and contraction going on at the two far ends, but we've also got to try and create this moment connection at the middle between the two moving spans, and that's fundamental to be able to carry the load structurally. And we also need to provide vertical support. And the moment that we're trying to carry is 3,500 kilonewton meters, which is quite a sizable amount. And it also needs to accommodate thermal expansion and contraction between the two moving spans. Now, normally you could put just a massive pin in, but the problem is that could well end up getting stuck at some point, and it's a known issue in swing bridges if you've got a big pin between the two spans, and I believe there's possibly been problems in the past in Copenhagen with that. So we needed to find a way of carrying movement across that joint that also allowed thermal expansion. And one way to think about that is to think of the fact that when live load's applied, it's going to be creating compression at the top of the beam and tension at the bottom. And that kind of simple way of thinking about it effectively allowed us to use proven technology, but in a new way. And a lot of the kind of creative and innovative elements on from a mechanical point of view, at least on this project, is this moment connection. So we've got this joint here that isn't a curved joint, it's a staggered joint. And in one span, we have a compression pin driven by this large yellow hydraulic cylinder. And then we also have a tension element that has effectively like a hammerhead on the end of it. And that's pulled back by the second lower hydraulic cylinder shown in yellow here. And then on the opposite span, we have this very shallow green socket, and it is shallow so that it has a very low risk of getting the compression pin can get stuck. The pin isn't a tight fit. It has a slight cut to it to allow it to provide the vertical alignment between the two decks, but it isn't a pin that kind of engages deep into the socket. And then there's also this mouth that the hammerhead on the other span can pull back against. So as the bridge swings round, the socket and the hammerhead align, and the compression pin is positioned directly opposite its socket. And then if we look at it in kind of cross section, once the decks have swung back to their closed position, the compression pin extends, and that provides the vertical alignment. And then the tension, so there's the vertical alignment's achieved on that socket, and then the tension element pulls back, and that then that pressure is then held in. So the hydraulic cylinder, the hydraulic pressure in the red elements is then locked off. The key element, though, is that the joint needs to be able to expand and contract. And what we want to happen is, as the compression pin gets squashed and pushed by thermal expansion, we need the tension element to effectively keep tight as well. And to do that, the hydraulic cylinders, the tension and compression elements are linked together, and the oil in the red section is joined together effectively. So as one expands and contracts, the other one moves by the equivalent amount. So the cylinders are the same size, are the same bore, same stroke, and they pull and push in unison. The other thing we have to be able to accommodate is, as live load is applied, we need to be able to effectively increase the capacity of this moment connection. And that's done effectively just by the pressure in the system will rise up as the live load varies, or as the live load goes up, the pressure goes up, and as the live load reduces, the pressure goes down. So it's effectively, without needing any power applied, it's a passive joint that is constantly adjusting to the load that's applied to it. It also allows the thermal expansion. So as we just said, the oil is kind of transferred backwards and forwards, and you can see there it's kind of shaded out as the two need to move. They can adjust to suit each other's position. This is what the equipment looks like in real life. You can see there's a power pack that this is all built into the side beam of the deck. There's a power pack below a hatch, and then there's also these tension and compression elements on one span. And that's what the joint looks like when the pin's engaged and the tension element is engaged too. So if I hand back now to Simon, we can carry the talk on.
Thanks very much, Mike. So just one other benefit of this moment connection was improvement to the dynamic response of the bridge. So obviously, with deflections and being limited by the clamping action of the moment connection, that was a big benefit. It meant that we were able to meet all of these criteria, the dynamic performance. Also, the flow of oil between the top and bottom section of the top and bottom cylinder under axial effects would also effectively be a viscous damper as well. So actually the dynamic performance of the bridge is further enhanced. I'm going to go on now just to talk about how the bridge was fabricated, constructed on site. So this is an image from CIG's workshop, which shows the double curvature of the outer plates of the box sections being put into effect. Very high precision was possible with this. All of those plates are 15 millimeters thick, just to make them a little bit easier to form this curvature, and additional stiffening is added inside the box sections where necessary, rather than making the outer walls thicker. All of those curved pieces and other sections of the bridge were delivered to the fabrication yard almost as a kit for Hollandia to weld together. And in order to do that, they had to build a jig, which was almost as complicated as the bridge itself. So this is what forms the shape of the bridge section. The jig allows the plates to be laid out and all of the welding to be done. Most of the welding was underneath the bridge structure, so the fabricator elected to build the bridge upside down, which then meant that each of the bridge sections had to be picked up and turned over, as you can see here. So that was another load condition that we as designers had to consider. We also designed the attachment points, the lifting points for the bridge section to enable this operation to be carried out. You can see the high performance paint system having been applied to the bridge sections, and all of the bridge sections were trial assembled at Hollandia's workshop on the quay edge, so that any adjustments to the alignment and the geometry could be made before bringing the sections to site. One of the key things was the balance of the moving sections. So as I mentioned, there's counterbalance, counterweight in the back of the swing sections. One of the ideas behind that was that there wouldn't be a net overturning effect when the section was landed on the pier, so we wouldn't have to hold it down in a temporary state. And there were measurements made of the the balance of those sections, just to make sure and there were some adjustments necessary to ensure that it was correctly achieved. So the bridge was delivered to Copenhagen from Holland on a barge over sea. So great advantage of doing that is that most of the work was done in factory controlled conditions, less weather dependency, much safer operation because the work was all being done in the workshop rather than out on site. So this is an image of 2 of the sections being lowered onto the barge. So actually all 4 sections were placed on one barge. Sections 1 and 3 were placed on the barge on the 16th of April 2018. And then a disaster. The crane that was carrying out the operation to place the subsequent 2 sections of bridge on the barge on the 18th of April collapsed. So it was a failure of the crane. Second section of the bridge fell on top of one of the other sections, and the jib, the yellow jib of the crane, fell on the other section that was on the barge. So there was significant damage to 2 of the most critical sections. Well, the most complicated sections of the bridge were damaged beyond repair. One section could be repaired and one section hadn't been placed on the barge. But overall, this crane collapse led to a delay to the project of a year. Hence my initial comment about the original date for completion being in 2018, and it ultimately ended up being in 2019. As I say, it was all down to a failure of a weld on the crane. So at the base of the jib was held up. The cables that were supported by the jib were anchored on the deck of the crane, and a failure occurred there, and the jib came down. Actually, the bridge section was only 100 millimeters above the steelwork on the barge when the collapse occurred, but even so, there was enough force generated to cause significant damage. And it was very fortunate that nobody was seriously injured in the accident. So a great tribute to everybody, I think, that the project was put back on track. The sections of steelwork were remade, and a year later, the bridge was brought to Copenhagen across the sea from Holland. You can see the tug pulling the bridge sections into sight, and a different crane following on in order to erect the bridge. So the supports had already been in place for a year. They had all of their mechanical parts already installed, the slewing rings, the motors, all the other equipment was already there. The vessel collision protection system, everything was ready for the steelwork to be erected. This is the same aerial view that Mike showed of the inside of one of the moving piers. Quite a nice view, show all of the mechanical parts, almost like the inside of a watch. And there we see more drone footage, this time of the crane picking up the bridge sections and placing them. I think the overall bridge installation it took about 10 days, if I remember rightly, which was pretty good pace for placing all 450 tons of steelwork over Copenhagen harbour. And commissioning of the bridge then took place. There wasn't much else that needed to be done once the steelwork was there. Just testing, commissioning, and finally the bridge was opened officially on the 14th of August 2019. Here you can see the opening ceremony. And some of the pictures of the bridge in use. Tall ship going through. The parapet of the bridge incorporates lighting. So half of the LED lights in the railing of the bridge point inwards to provide the task lighting of the walkway, and half of them point outwards to allow feature lighting to be applied. And this is an image that comes from, I think, a festival of lighting in Copenhagen, where there was some nice lighting effects produced. So just to draw things together with some concluding remarks, I think it's a pretty unique project, I must say. Quite inspiring. The most innovative feature of it is this central moment connection. Enables the bridge to be more slender, more efficient. As Mike said, it uses proven technology in a new way. And I think the quality of the construction is also extremely high. It's always nice to know that the skill to construct structures of this nature is still exists. And a lot of attention was given to detail, particularly construction tolerances and so on, so that when the bridge was completed in the workshop and brought to site, there weren't any problems with things fitting. Just a closing image of another image of the bridge as it's opened. Okay, on that note, I'll hand back to Jan to see if there are any questions.
Thank you, Simon. Thank you for the very good and interesting presentation. I see we made the right choice when we chose it as the 2021 structure of the year. We have a question from Lynn van Wentner. And the question is, what is the power source for opening and closing of the bridge sections?
So the bridge is powered with 4 electric motors, and that power is brought in under the water from the main Langebro bridge, which is also where the Lille Langebro is controlled from. So it's electrically powered, but there are hydraulic elements at this moment connection because of the need for very high forces.
Yes, so the Langebro bridge nearby is also a bascule bridge that can open actually, and that's where you got the power supply. Yeah.
Correct. Yeah.
Great.
Yeah, so this is the control tower. It's actually ideally located for our bridge as well, which is obviously not in this image, but is just on the same side of the bridge of the Langebro as the control tower. So we actually have an additional control panel installed in there, and there are underwater cables that come from the Langebro across to our piers.
Yeah. We have another project, another question, and simply, what's the weight, kilo per square meter? You know.
So it's 456 tons of steel, and only a very thin resin-bound surfacing on top. So it's pretty much, not a great deal more than that. Is the answer.
Yeah.
It works out at 263 kilograms per square meter as a steel weight, which, bearing in mind it has to work as a cantilever, is reasonably efficient. structure.
Yeah. So we're getting a lot of questions now, which is good. It just shows that, yeah, interesting presentation. About the foundation of the bridge, Vidi is asking whether it's a pile foundation or how is it?
So we had pile foundations at the abutments, where the abutments themselves are quite shallow. So we piled down to good ground. Whereas within the harbour, we placed cofferdams and excavated inside the cofferdams until we found competent ground within. From memory, I think it's glacial till is the founding material. And then fill material was placed on top of that inside the cofferdam, and then a concrete foundation built on top of that, quite a deep concrete slab inside there. And then from that, we built the sort of concrete piers which you see above the water.
Yeah. That makes sense. I guess the expected settlements are little to none for a bridge like this. I have a question of my own, actually. Michael, you talked about the bridge transferring moments at the middle of the midspan, and that, among other things, that was one of the things that impressed us in the Danish national group when we chose Lille Langebro as the winner in 2021. How did you guys come up with that?
So I think one of the rules of the design competition was that they didn't want big pins. We weren't ever quite sure what the reason behind that was, but it's fairly common to have concerns over kind of locking pins and big sliding elements going backwards and forwards. And I think Simon pointed out that in structural terms, what we need is something to push at the top and pull at the bottom. And I think that was the kind of spark of the idea came from that initial meeting. And then we talked about how we could have some sort of mechanism that pushed and pulled. But the thing that was always nagging in my mind is how do we get it to adjust for the thermal movement? So as the deck gets closer and further apart, and then on some of the other projects we've done, we've connected cylinders together so they all move. But what I realized was if we connected the front of one cylinder and the back of the other, they'd actually all move together. So as they needed to tighten up, the one that was already pulling quite tight would pull tighter, and the one pushing would start to push more. So it was a kind of spark of an idea, mulled over and different options, and then trying to work out a way of trying to keep it really simple, because we know for moving bridges, the simpler we can keep it, the more reliable it's going to be.
Yeah, thank you. Raed is asking whether you've heard anything from the operation of the bridge, whether it's still functioning as planned, or are there any lessons to be learned?
I have a Google alert, so I keep track of all of our projects, and it very, very rarely comes up, and it's normally because there's some event going on across it or a lighting thing, as I think Simon showed. So not living in Copenhagen, I can't be sure, but as far as we are sitting over in the UK, we've not heard of any substantial issues with it, and normally people get in touch if there's a problem. So yeah, fingers crossed, no news is good news.
Yeah, well, me neither. So, but I would guess at one point Copenhagen Marathon will probably cross it.
That'd be good.
Yeah, and on that note, Simon, you were talking about vibrations and accelerations of the bridge deck. Do you know which assumptions was used regarding that connections in midspan?
So it acts fully as a fully fixed connection for moment, and it's axially released. However, there will be some. It's a little bit like a shock transmission unit, because any instantaneous loading will not be. It will take. There will be a finite time before it gets relieved. So it's great for thermal movements, because that is relieved by the flow of hydraulic oil between the top and bottom cylinders. But any sort of dynamic loads will be resisted. So, we looked at both extremes of axial released and fixed condition. When it's fixed, it gives big advantage in terms of the dynamic response, although it's also acceptable if it's released. It'd actually be something I'd love to be able to do some tests to really quantify the effect. If we could get a university project or something like that to look at it, I think because I really think that the joint has got other benefits to it.
I would guess that it's not too straightforward to predict the response precisely.
Yes, that's right.
Raluca is asking what the finite element analysis software that was used to design the bridge.
So I think most of the work that we did was in LUSAS. So we set things up so that there was a Rhino model of the structure, and that was linked to LUSAS. So things like the shading study that I mentioned, we could get the two software to talk to one another and create the loading pattern that we were trying to analyze. We did the global modeling, but there was also lots of local models, because there are areas that require particular attention. Local loads where we've got bearings and so on.
Kieran is asking, how is maintenance performed on the rotating foundations? I guess it's the mechanical.
Yeah, so there's hatches in the deck which have access. In fact, you'll be able to share the screen. So there's an access hatch within the deck that allows you to drop down onto the top of the rotating, the two piers that have the slew bearings in them, and then within them there's another access hatch that you drop down. So it's all accessible effectively from land. You don't need to get in a boat or anything to get access to maintain it.
Jorge is asking what the minimum and maximum structural depth of the longitudinal boxes is.
Okay, I can just put an image back up, I think, of the... Okay, so these are some typical sections. So actually, no point is the box so high that you can't actually see over it. There aren't dimensions on this, but the parapet is 1.4 meters high, so you can get some sort of idea. It's maybe 1.6 above the deck level, and then so perhaps 2 meters measured vertically is sort of the highest dimension.
We have another question on natural frequencies again, but if you can remember what the natural frequency in the transverse direction for the first mode is.
So that would be well above the normal threshold of 1.5 hertz, because it's actually very stiff laterally. We have all of the section is on the outside of the structure. As you can imagine, it's 7 meters wide. So actually, laterally, it's much stiffer than it is vertically. Actually.
And Vidi is asking, how about this failure of the crane? Were there any problems on that, regarding contracts and needing to to prolong the building for a year? how was that handled?
Well, I wasn't involved in it in great detail because it was really a matter for the fabricator and the
Yeah.
crane company. So I don't know too much about the details of it, but obviously it was at the time it was a pretty stressful situation to have to go through. As I say, it's great that nobody was seriously hurt by the incident, and it was, apart from anything else, there was a lot of hard work had gone into the fabrication. People had been working, round the clock to try and get things finished on time, and then you can imagine what it's like when something like this happens. So it's amazing that those people were able to do all the work again.
Yeah.
It was fortunate that they were able to refabricate it within a year. I suspect it must have been quite disruptive for the fabricators to have to reaccommodate building two of the spans again. Must have been very disruptive.
Yeah, that's right. And I mean, one of the sections was actually repaired. It wasn't damaged so badly. But the two most important sections, the two moving parts, both had to be completely remade.
Yeah. We have another attendee asking which building codes and national annexes were used for the structural design.
Well, it's all been designed according to the Danish version of the Eurocodes, primarily for the steel 1990, EN 1993.
Are there any special challenges working with the Danish national annex you remember, or differences to previous experience?
Well, we do have a office in Copenhagen and do projects in Denmark, so it wasn't a complete surprise to us. I can't remember. I think there are a few subtle things, but there's nothing that really sticks in my mind as being a big issue.
Good to hear. And last question is from an attendee. Is there any hinge joints at the expansion joint location? Probably.
So yeah, there are some deck flaps that cover the thing, and again, we might be able to just, if I can show my screen. I think one of these images has there. So there's these flaps. This one was just propped up. This photo was taken during commissioning, but there's this row of deck flaps that run up a shallow ramp on the front edge of the fixed span, and they expand and they move with the deck, but provide a kind of smooth surface to transition across the joint, and that's what accommodates the kind of vertical movement as it swings round, and then provides that transition surface.
Yeah. And the last question regarding just another one come in. So did you have any difference or difficulties when designing the midspan joint due to temperature variations of the deck?
So I think quite a lot of Simon's work was looking at what the differences could be, and then the joint has a guide on the leading edge. It wasn't shown in the presentation just for time, but there's another, similar to the socket that's at the tail span, there's another small wheel that comes in and just provides an initial alignment between the two moving spans to get them closely aligned, and then this compressive pin provides the last bit of alignment.
Yeah. And the last question, no, still, it's good. Still questions coming in.
I think we know the author of this one, but let's ask it anyway. Go on then.
Okay. It's from Simon asking who specified the car park barriers on such a beautiful bridge.
Was that the
architect?
Who was the architect, Simon?
It was a chap called Simon Roberts, I think.
Probably a lot
Yeah.
of debate went into those barriers. Eden had designed a nice set of kind of bespoke barriers, and I think other market forces within the project meant that we had to go for something slightly more, slightly less bespoke, and partly, or probably significantly less acceptable to the architect. But it's good to see Simon on the call, and visually, I think he's done a great job of the structure. And hopefully, people would say that they'd not even noticed the barriers at either end.
Yeah, I would say it's a beautiful bridge, and it's very comfortable and easy to cross when you're riding a bike, compared to some of the other bridges across the Copenhagen harbor. So I agree to that one. A question regarding the initial considerations when you were doing preliminary design, whether it was ever considered to use timber instead of steel for this bridge.
Well, we at the competition stage, we wouldn't rule anything out, and we were always looking for opportunities to use timber, but in a marine environment, it's challenging to meet the criteria for design life, unfortunately. So I'm sure we would have thought about timber and whether or not we could get it to work. There's a 35-meter navigation span, so any timber structure would be considerably more bulky than the steel structure. So I think it is good to try to use timber as much as possible, but this probably wouldn't have been the right project for that.
Yeah. So there's a question from Raed regarding the pedestrian barriers. That they're, I think the question is that they're a bit inclined and taking a bit of space from the free width, whether that was planned or not.
I can't remember actually. We always had pedestrian barriers of one form or another, which would have occupied some of the free width.
I think it was planned, wasn't it, so that it accounts for that width as we go past the bearings. There's a slight narrowing, but it is. There has to be something there.
I think the bridge is slightly wider than the minimum 7 meters anyway, because if I recall that the dividing strip in the middle is additional, so there is a little bit of extra width. But whatever it was accepted that if that the local reduction was okay.
And a last question, I think, also from Raed. Did you do a CO2 impact calculations for the bridge?
Yes, we do that as a routine now on all of our projects. So we've got an embodied carbon calculation. As I say, the steel weight is reasonably efficient given the demands on the structure. So I think it stacks up quite well when benchmarked against other structures.
Yeah. Great. Thank you so much. There was a last question about to explain that moment connection in the middle of the deck again. But I think we should say that this has been recorded, and you're able to find the presentation on our IABSE's homepage again. And if you go to the middle of the presentation, I think the explanation was quite good. So I don't know if you have any final remarks, Michael, Simon.
No, just to say it was a tremendous project to be involved in. Amazing team, and it's so nice to see it being realised. We actually took the whole of our bridge team for a visit there earlier this year, and so it was nice to see it again.
Yeah.
I think
Great.
it's been a really good project, really nice city as well to have been coming backwards and forwards to for the few years whilst it was being designed and built. So yeah, we're certainly everyone at Eden, and I'm sure Simon agrees at Bureau Happold's very proud of the work and how well it's been built and manufactured.
Yeah, you can be, definitely. Thank you so much for a very interesting presentation, and again, congratulations on your 2021 Structural Award from the Danish National Group. Thank you.
Thank you,
Thanks
everybody.
very much. Thank you.